Okay, good day, greetings. Okay, today we are looking at periodic table, and what you need to understand on the periodic table, you need to understand that this is our metals, and these are our transition and transition. So we've got metals, then we've got transition elements. Then here we've got what call the metalloids. So metalloids, the metalloids are your boron, silicon, and from there we have got nanometals. So here these are your metalloid, and these are your nanometals here from group 4 to group 7. Now on this last part here, we call these noble gases, and these are unreactive. Unreactive, because we are saying they are very much stable. They are stable. Why? Because the outer shell is filled with electrons. I will explain to you what I mean by that. Now, so in general, and here when you're looking at each and every atom here, you see that there is it shows you what called electronegativity. We're going to look into that. Then atomic number, which is your number of your protons. Okay, then we're going to explain that so that you can understand. Now let's check here periodic table, what it is. It displays the elements in increasing atomic number. Okay, increasing a proton number of protons. So atomic number is actually your number of protons. Okay, now when you're talking of protons, this is a positive positive charge. Increase in the number of positive charge, you will understand how it affects them. Now the table can also predict properties and of elements, even those that have not yet been discovered. So we can actually determine their properties as well. Now let's check with what do we call a group. A group is the one that goes these columns. These are the what you call groups. That's what we refer to as groups. And so we can say group is going down. It's going down. Then a period, what we refer to as a period, is actually going from left to right. So group top to bottom. What is it? Then a period left to right. That's what we refer to as period. So if that is to ask you to describe the what called the change or in the period, you must always know that you're moving from lithium maybe to what called to fluorine there. Okay, so that's what we call a period. Then let's just have to what call familiarize with what called the terms. Atomic radius. So atomic radius is a measure of size of an atom. Then we have got ionization energy is the what call energy needed to remove an electron from an atom in a gaseous phase. So that's what we call ionization energy. So we've got the first ionization energy when maybe your sodium lose one electron. When we've got the second ionization energy when your magnesium what you call lose two electrons. So we can say first ionization energy is for the sodium. Then also the second ionization energy is for magnesium, because magnesium is to lose two electrons. Now, then electron affinity can be thought of as how much an element wants electron, how much does it want electrons, and we're going to look into this as well into detail. Now electronegativity is the tendency of atoms to attract what we call electrons. So we are saying when atoms are bonded together, let's say we have a molecule of water molecule here. We have got hydrogen, oxygen, and hydrogen here. Now H2O. Now here on the water here, you find that your oxygen have got high affinity, high electronegativity, what call compared to what call to your hydrogen. It needs electrons more than your what call your hydrogen. So your hydrogen, even in that sharing, they are sharing, but the electrons are more attracted to the what to the oxygen. So this one becomes later negative, meaning slightly negative, this one slightly positive, this one slightly positive. You actually have to understand this later on. But now let's understand something here before I go into detail. We need to understand the atom, how it behaves. Now let's have a general atom here. So we are saying here we have got the nucleus, which contains the positive, so which you call the nucleus. So this is our nuclear, and we can say we refer to as nuclear charge. So your nuclear charge increases, so increases across the period. So we are saying it increases across the period. That's what you must remember. Then, but now what happens is that we have got these outer, what you call these electrons. So we've got outer, what is it? What you call outer what electrons that are actually attracted to the center there. So let's give an example of lithium. Lithium, we have got how many electrons? 3 electrons. So here we have got one. The first shell is only filled with 2 electrons. So the stable, what is it? Gas here is helium, which have got only 2 electrons on the outer shell, which is fine. The first, we call this energy levels. So go to another energy level. And this energy level, we are going to add 1 electron. We're going to add 1 electron. But now what happens is that in that same period, in the same period that we have lithium, beryllium, boron, carbon, sodium, what we are actually doing, we are only adding electrons. So this is level energy 1. This one is N2, energy level 2. Now, what happens that what we're just doing, it is filled with what? 8 electrons. So it's full with 8 electrons. The first energy level is filled with 2 electrons. So what happens when we are just, what we are doing here in the same period, we are just adding electrons. So from there, this is lithium only. Then we go to beryllium. Now, what are we doing? We are adding another electron in the same shell. Then we're going to boron, we add another electron. We go to, so we are saying lithium, beryllium, then we go to boron, we go to carbon, we add another electron. Then what do? We go to sodium, nitrogen, we add another electron. We go to oxygen, we add another electron. Then what do? We go to fluorine, we add another electron. Then we go to neon. Now, neon is now, you have got all 8 electrons. So can you see what we're having here? We are adding all electrons. But remember, when we are adding that, we are also adding the what you call the positive, the nuclear charge. So the number of protons are also increasing. As we add electrons, we are also adding protons. So what happens now is that these electrons becomes more attracted to the center, to the nucleus, because the nuclear charge is increasing. So what happens now is that you find that things like atomic radius, they decrease as you move across what you call the period. That's the reason here. But now let's see what happens when you are to add an extra, when you are moving down the group. So this is moving in the same period, but now going down the group, what happens? We are adding the extra shell. We will be adding the extra shell. So we are saying this is your lithium here, but when we go to sodium, we are adding another shell. And when we add another shell, these electrons are now far from the nucleus. When they are far from the nucleus, they are less attracted. When they are less attracted, it means that now this sodium here, for it to be stable, it will rather lose electron and attain the structure of what? Of neon. So we are saying in that case, it doesn't need electron. It doesn't need this out electron. So we are saying now its electronegativity or its affinity is actually low compared to what called to something like chlorine. Because chlorine now will say, no, I would rather gain electron, because we are saying when you have fluorine is just left to gain 1 more electron to attain a stable state of neon. So what will it do? It will rather gain the electron than lose it. So that's what we call we talk about electronegativity, we talk about electron affinity, how much it wants the electron. We find that electron affinity increases as you move from left to right. A negativity also from left to right. That is the major reason there. But you need to understand the nuclear charge and the addition of extra shells. So going down the group, we are adding what? Extra energy level or extra shell. When you add extra shell, the electrons are less attracted to the to the nucleus. So the nuclear charge in that case, it doesn't have much effect. But Moving across the period, what we are doing, we are increasing the nuclear charge. When increasing the nuclear charge, we still have the same energy level. And what happens now? Electrons are becoming more attracted to the nucleus. Okay, so I hope you guys understand this. I will send this also in your notes so that you can understand clearly. So here, what is it? Let's move on to the to the next page here and see what I was actually telling you. Now, remember, we say these are the only stable gases. These are the only stable gases, and they don't react. But all other elements here, what do they have to do? They have to either gain electron or lose electron to become to attain the the stable state. So like sodium would rather lose the one electron and attain the state of neon, which is stable. But chlorine will say, no, I'm going to gain one electron so that I can become argon, which is very much stable. So that's what happens. So chlorine, so these ones, they tend to gain electrons than lose. They tend to gain more electron than losing to attain the stable state. The metals tend to lose electrons to attain the stable state of gases. So this is what I was just explaining here. You actually get to understand when you are reading as well. Now, also, another thing, valence electrons, which are outer electrons, they are the only ones that are involved in the in the chemical reactions or in bonding. Now, and another thing that we need to understand, group 1, which are your lithium, sodium, these are alkali metals. We refer to them alkali metals. Then group 2, we refer to them as alkali earth metals. Then these ones are transition metals, but we're not worried about them as much. I think I've explained this on this part here. And halogens, which are your group 7. So we don't need to worry much there. Now let's move on. Now, here we have got the S block and D block and P block. What does this mean? Here it means that the outer electrons or the valence electrons, they are in the S orbital. They are in the S orbital. Then in the in the nanometers here, we say that we call the P orbital, meaning to say the outer electrons, they are in the P orbitals. The S orbital is already filled here. The P orbital is the one that is still empty. So they still have to fill the P orbital. Okay. Now, let's move on to the density. Now, density of of your elements. How does your density behave in the in the period? Now, I find that from group 1, group 2, group 3, what happens up to group 4 here? What is happening here? That the density is increasing. The density is this now has to do with bonding. How closely, how pegged your atoms together. So here you find that they are much pegged together because of the bonding as well. Metallic bonds, they are quite strong compared to covalent bond. So here, this is what the reason why we are having increase in the in the density and decrease in the density on nanometals. Now, when you move on to melting point and the boiling point. Now, remember what I said here when we are having atoms, when we are having the bond that we have here, we have mainly here, we have got metallic bond. So in this case here, we have got what call metallic bonding. So these atoms here are closely pegged together and they are strongly pegged together. They are closely attracted to each other. So that's why we have got increasing high boiling point here, or the melting point, because to change the state, you actually need to apply more high temperature. But here now, we see that here we've got covalent bonding. Covalent bonding, which doesn't have a specific structure that are actually strong. The only exception is carbon. Your carbon is high because you find that how it is structured, how the atoms are pegged, like example diamond and what called graphite. These are actually strong and they've got high boiling point and high melting point. For example, diamond, this one doesn't have it's not a metallic bond, it's actually a covalent bonding. So that's what you must understand. They would only the carbon is actually, and silicon, this gives you high boiling point and melting point. But Other nanometals here, you find that they actually have a low boiling point because of the what you call covalent bonds. And as you can see that chlorine as well, here you have also what you call a low boiling point and melting point. Okay, now let's move on to atomic radius. Now, atomic radius, what did I say? Atomic radius, we are saying when you are moving from lithium, sodium, and what is it? Potassium. Can you see what's happening? It's increasing. Why? Because we are going down the group. Down the group, what is happening there is that we are adding an extra shell. We are adding, so from there, lithium, you have got one, let's say here we are saying it have got two shells here, two shells here. But when you're moving to sodium, we are adding another shell. And when we do that, these electrons, other electrons, they are less attracted. That's why you're saying atomic radius is actually increasing. It's actually increasing going down the group. But when you move from lithium to fluorine, here what's happening that is that here is only in the same what? It's only in the same, we are still in the same energy level. So this is the same energy level. So here is energy level 2. But here we're moving on to energy level 3, but it's still 3 here as well. So it means that we are still keeping the same energy level and same electrons, we are still having the same nucleus, but what you're doing, the atomic number is increasing, meaning the nuclear charge is increasing. So here we are saying because the reason why atomic radius is decreasing because of the nuclear charge increasing. Nuclear charge. That's why why we're having that increasing nuclear charge. But here now we are saying it's increasing here. Atomic radius increasing. Why is it increasing? It's increasing because of what you call additional energy level. And now electrons are far from the from the nucleus, so they are less attracted now. As we move on to sodium to potassium again, you find that we are adding another shell again. It goes on like that. But here we are actually in the same energy level, but what are we increasing? We are increasing the nuclear charge. Nuclear charge, when increasing nuclear charge, we are more electrons become more attracted. Electrons more attracted. So when they are more attracted, it means that they're actually more attracted to the nucleus. So it actually becomes small and small, what call the atomic radius, okay? Atomic distance from your nucleus to the outer shell there. It actually decreases as you go on like that. This is what you're supposed to read as well. What is it? In the notes, but I hope this explanation is actually clear. Now let's see what happens now. We know that we what call halides. What call halides? Remember what we said? We said halogens, and halogens are your fluorine, chlorine, bromine, and what is it? And iodine. But these also, they bond with our metals. They bond with the metals, and when they bond with the metals, they form what call metal halides or metal salts known as what call halides. So here is an example here. When you're saying your lithium, you have got, has to donate what? How many electrons? 1 electron. And your chlorine has to gain the what call, is actually in short of the electron, so it becomes negative. It's -1, chlorine negative, meaning to say it's gaining the electron. So in that case, what form the lithium chloride? So you must know that your beryllium, and when we talk of what call beryllium here, beryllium you've got two electrons to donate. When you have got 2 electrons to donate, what does it do? Chlorine only need 1. So you find that group 2, when you're talking of what called the group 2 now, you find that they bond with what called with the 2 halogens, with the 2 halogens atoms, because they are donating 2 electrons, and each halogen atom need what? 1 electron. That's why we are having 2 here. So we are saying it's actually beryllium is donating what? 2 electrons. So it's saying I'm giving you guys 2 electrons, but chlorine is saying we only need 1 this side. Chlorine only need 1. Chlorine only need 1. So what happens is that chlorine here, will say chlorine negative, plus your chlorine negative. Then because they are gaining 2 electrons, this one only need 1 electron, this one only need 1 electrons. That's why we are saying it's gonna beryllium what you call you've got two chlorine there. Now let's move on to group three. Group three again, remember they are donating how many electrons? 3 electrons. And how many halogens do we need? We need 3 halogens. So don't, please, you must always remember this when you're actually asked to determine maybe the chemical formula or what called the compound formula formed. You must always understand when you have combining metals and halogens, what is the ratio there. You must always know the ratio. The ratio is all come from how much is donated and how much is needed. Now oxides also are formed, so it means that the oxygen also react with your metals, with the metals, to form what called metal oxides. Now it all again depends with the what called valence electrons. Remember, your oxygen, it requires how many? It requires 2 electrons. So oxygen here, halogens need 1 electron. Oxygen need 2 electrons. That's the difference here. So lithium only have 1. So how many should we bring here? We should bring 2 lithium. That's what you need to understand here. But sodium, you see, we only donate 1. How many must we have here? We must have 2 sodium. Now again, potassium. But when it's beryllium now we know that beryllium donates what? 2 electrons, and oxygen needs how many? 2 also electrons. So it actually squares there. So you've got beryllium oxide like that. Now that's what you need to understand here, guys. You just need to master this part here, and it depends also. Just know that my oxygen needs how many electrons, and what is being donated here is actually like that. That's how the ratio goes. Nanometals also react bond with oxygen, guys. Nanometals also bond with oxygen, like your carbon bond with what? Bond with oxygen and form carbon dioxide, and can also form what called carbon monoxide, can form carbon what called dioxide, depending on how much is being shared there, how many electrons are being shared there. Now, so this is what you need to understand. You just need to understand this table as well. Now let's move on to ionization energy. Ionization energy, we are saying the amount of energy required to remove an electron from a neutral atom. Now I want you guys to understand something here. You can see that there are ups and downs here. There are ups and downs here, and these ups and downs tells a lot of things here. Remember, when if you understand the electron configuration, we said you have an orbital, and the s orbital is filled with how many electrons? 2 electrons. Then you've got the p orbital is filled with what? 6 electrons. So now I want you to understand something here. Now here we say that these electrons, they do what you call, this is the p orbital. Now these electrons, they do repel each other. You understand? They do repel each other, and this, when s orbital is like this means that they are actually more stable like this. But now let's check here and see what's going on. We have got the helium, it's fine. We've got the high ionization energy, because to remove that those 2 electrons, because they are already what called in the stable, and to remove that, you find that helium, neon, argon, these are noble gases. They've got filled what called outer shell, meaning to say they are the p orbital, the s orbital, they are all filled. In that case, now we are saying they will not lose, they can't just lose electrons. So in that case, we will need high energy to remove what called the electron. But let's go on to lithium. Lithium, you find that lithium only have got an extra electron, so it have got 1 electron. So lithium, in this case, the valence electron is only 1 electron. So this 1 electron is quite easy to be lost in the valence, So it's quite easily what you call removed. That's why we see that NCN is very low. But let's go to beryllium. Beryllium, we find that it's actually having 2 electrons now. You have got 2, how many electrons? It's have got 2 electrons. Now this one is a pair in the s orbital. It's a pair that is there. But let's go to boron. Boron now is got low ionization energy, but we are expecting our ionization energy to increase across the period. But why now boron have got, what is it, less? Is it because boron now, what does it have? It have got this. It have got s orbital. it have got 3 electrons that are outer electrons. But now those 3 outer electrons, now what happens is that these 2 electrons, they are fine in the s orbital, but there is 1 electron here. So now look what happens. This actually is can be repelled here. It's actually, it can be lost easily. It's easily lost compared to what? To beryllium. Beryllium, these two are quite fine here, but here this one is alone. So it's actually can actually be easily what called lost. That's why we are saying it will actually be. That's why we're having a low. That's account for the low what you call low boiling, low ionization energy there. Then goes on again to this oxygen and nitrogen as well. It also goes along with that. With the nitrogen have got also nitrogen have got. Let me check here. Nitrogen have got how many electrons? They have got 5 electrons. So if you have to check nitrogen and we check with oxygen, now here nitrogen and oxygen, we have got the p orbital. So the s orbital is already filled. So we're just focusing on the p orbital now. How is it what called structured there? So we have got this, we have got this. Now we are saying how many electrons for the nitrogen? For nitrogen, it's 5 electrons, outer electrons. So when you're saying it's 5. And we are saying 103, then you say, remember it must face down, opposite spin. Now these are 5. Then when you check with no. Here we have got 2. It means that we need 3 here. Sorry. Just allow me to rub here. So 5 outer electrons, it means that here we have got 2 and we're left with 3. So we need to put 1 in each. Remember, 1 in each. So when you put 1 in each, it's fine like this. But now let's check with oxygen now. Oxygen, what do we need to have? We need to have 6. So we are adding extra 4 here now. So in this case now, this becomes this, what this have now is that these 2 electrons, they actually are repelling each other now. They are repelling each other now. That's why we are saying here in this case here, this is more stable. That's why it have got high what you call ionization energy than oxygen. Oxygen now, because these actually repelling each other now. That's what's happening there. They're actually repelling each other now. These ones are very much fine on each its own orbital. That's what's happening there. Okay. Now let's move on to what is it? Let's move on to so here what you need to understand: ionization energy increases what call what was in what call across the vertical. So ionization energy, what's happening there is that it's increasing. Ionization energy is it's increasing. All right, ionization energy, you find that ionization energy, what is happening there? It's increasing across the period, increasing. Then, but what happens to it now? Down the group is decreasing. Down the group, as you can see, it's decreasing. It's decreasing. Why is it decreasing? Because remember what we said again from that start with your electrons, they are less attracted when we add an extra shell. When you add an extra shell, what happens to your electrons? They are less attracted. That's why when you add an extra shell, they're less attracted. So going down from lithium to sodium, ionization energy, this sodium it's actually quite easy to remove this electron than lithium, because we're adding an extra shell and it becomes less attracted to the nucleus. That's why we're having that. That's why it's decreasing down the group. Now let's move on to electronegativity. Electronegativity here, let's check electronegativity and see what we are having, what we're having there with electronegativity. Now electronegativity, we are saying it's actually increasing. It's actually increasing from what? From lithium to fluorine. It's increasing across the table, across the period. Why is it like that? We are saying tendons of attract electrons. Your lithium, they would rather lose one electron that is on the outer shell than gaining seven more electrons to be stable. So they would rather lose. So when you go on they tend to need more electron to attain the stable state of argon and neon. So that's what we have. When you're moving across the period, that's what happens. The electronegativity increases, but it decreases going down the group. It decreases going down the group because again we are saying they don't need much electrons as we go down, because remember electrons are far away from from the nucleus, and they are not attracted there, so they would rather lose the electrons than than gaining them. Then let's talk about electron affinity as well. We spoke about electron affinity. Electron affinity increases across across when you move from lithium to to fluorine. Why as well? We are saying the electron affinity tends to lithium metals tends to lose. They don't need electrons, tend to lose electrons than gaining them. So that's why we find that they don't want electrons. But oxygen, fluorine, they need electrons to become stable. That's why they're attracted to more electrons. That's why you see even halogens, your halogens, because they are the ones on the last, they are the ones on the last on the group 7. They only need one electron. So electron affinity for group 7 is quite high. It's quite high because they just only need one electron to become stable, to have a stable state. That's why we are having that. So it's all because of it goes on with atomic you have to relate the atomic radius, you have to relate to the mainly to the to the proton number, the nuclear charge, because the nuclear charge, these electrons, they are more attracted. So as you move on from lithium to fluorine, the electron, the nuclear charge increases. As it increases, it tends to attract electrons. It tends to attract electrons because it's still the same shell, so it tends to attract more electrons. Then let's move on to the last part here. The last part, we are looking at the group 1, group 2, group 17, and group 18. These are group 6 and group 8. Group 7 and group 8, your halogens. Now, let's check here. We are looking at how many electrons are in the valence electrons. So you find that here there is there is only one electron. There are only 2 electrons on the outer shell. And here we are having how many electrons? 7 electrons. Here we are having 8 electrons. So this one is full. This one is actually only need one more electron to be full. So you find that alkali metals, they tend to be more high reactive. So they are more reactive here. They are more reactive. I don't know the good word, more reactive. Yeah, more reactive because they just need to lose one electron. They just need to lose one electron. So when you move, what is it? Lithium, sodium, potassium. So it actually increases the reactivity. It increases going down the group because they easily lose the easier it is to lose the electron, the higher the reaction. Now, alkali earth metals, these ones, they are less reactive. They are reactive, but less reactive? Less reactive compared to your alkali metals. Less reactive than alkali metals. Less reactive compared to your alkali metals. So here you must know that they are very reactive, good conductors, but these are all good conductors. Your metals, good conductors of both heat and electricity. They also have low density. Remember, we say density increasing from your group 1, group 2, it's increasing there. Then in this case here, we are having, they are less reactive, and again, they are also good conductors here. And let's move on to the halogens now. Halogens here, we are saying the halogens, they have got what? They are in the group 7, And when they are in the group 7, they have got, we call them, they are nanometers. And being the nanometers, they have got low melting point, low. So these guys, they've got what? High boiling point, and melting what? Point. This one have got low melting point and what? Boiling point. So you find that they've got low boiling point and melting point. And also, what is it? The boiling point and melting point is decreases, what increases down the group. Melting point and increases down the group, increases down the group, because of the intermolecular force, they increase what you call going down the group. Noble gases, these are unreactive, very unreactive. They are very much stable. They don't worry. They are stable and unreactive because they've got a filled outer shell. Okay. So guys, I hope you guys enjoyed the lesson. I'll try to attempt some questions so that you can maybe understand much better. Okay. Until next time, guys. Thank you so much.